last Wednesday when I finally looked out of the window in the morning, I really felt like an idiot. Because it looked perfectly harmless. Nonetheless, then it was too late. I hope the stream was okay. Today I wanted to announce that I will have to finish a little bit earlier because I need to catch a train. But now I realize that the train is so much delayed that I have no trouble catching it, even if I finish the lecture in time. This is a good start. It goes on like this. Troubleshooting has completed. But the trouble hasn't. So I can't show you anything on this screen, which is not so important because we don't really urgently need that. I had the same problem on this machine, but this I could reboot, and I do hope it's going to work, the stream and the recording. All right. Given these preliminaries, let me start asking, do you have any questions on the upcoming exam? Is everything okay? All right. Good. Okay. So last time, what I tried to do on this, on the stream was that I wanted to talk about disks, essentially about two aspects of disks, namely, first of all, the relation between the surface mass density of the disk and its three-dimensional gravitation potential. And we saw it's essentially a Fourier transform, except that the base modes of the Fourier transform in that case are cylindrical Bessel functions instead of the ordinary Fourier modes. So far, so good. The next thing I wanted to speak about last time was the stability of disks against perturbation. Because what we very often see is disks in astrophysical circumstances. It could be galactic disks, accretion disks, protoplanetary disks, and whatnot. And very often they form bars, spirals, knots. In any case, they fragment. And the question was, under which conditions do they fragment? What stabilizes a disk against fragmentation? And what gives rise to enhanced fragmentation? And of course, gravity leads to fragmentation. And the internal pressure of the disk and the rotation leads to stabilization of the disk. And if you combine both criteria, you find tumorous criterion, which I derived using the hydrodynamical equations, just because that derivation is a bit simpler. But the criterion is not fundamentally changed. Okay, that's what I wanted to do last time. Do you have questions on that? Not the case. Then, this week is the last week of this lecture where we will talk about new material. And what I wanted to cover this week is, first of all, a process called dynamical friction. That's a very interesting process because you have a situation in which energy is conserved, and yet there is friction. How does that work? That's important, and we are ultimately going to arrive at Chandrasekhar's formula for dynamical friction. The formula has its problems. People have investigated certain aspects of its derivation. Nonetheless, I think you need to know. And first of all, you need to know about the process itself, right? Dynamical friction. Okay, let's see how far we get with that today. And nonetheless, even though my train is delayed, I will have to leave relatively on time. The other point that I wanted to possibly introduce this week, if there is time enough, is the Fokker-Planck approximation. It is one step going beyond the collisionless Boltzmann equation or the Liouville equation towards introducing collisions between stars or other components of a stellar dynamical system. So far, so good. That's the menu. So let's start. So we are going to speak about Chandrasekhar's formula for dynamical friction. The situation is very simple. You have a widely extended stellar dynamical system composed of small things. Could be stars, could be smaller masses. And then one particular mass is moving through that. And as it moves through this collection of objects, there will be individual two-body encounters, and they will deflect. So if you imagine sitting on the one, let's say, larger mass that is moving through that sea of smaller masses, then you see the smaller masses passing by. What do? Each individual one of them is going to fly past you on a hyperbolic orbit. And you know that from the Kepler problem. You have unbound relative motion of two masses with respect to each other. And so all the individual small masses will follow hyperbolic orbits and collect in your back. Right? So there will be, because of your motion through that sea of small masses, an enhancement of small masses in your back. And that will exert an enhanced gravitational force on you and slow you down. Okay? So that's a friction process that has nothing to do with conversion of ordered kinetic energy into heat or something. Mechanical energy in this circumstance is perfectly conserved, and yet you have this kind of deceleration process. And that's interesting because it, of course, depends on the mass, on the velocity with which you move through that sea of small masses. It also depends on the mass of the object that is moving through that sea. And it depends quite strongly on that mass. So that means that suppose you look at an object which contains a lot of small masses and larger masses with a mass spectrum. Then this dynamical friction process will give rise to mass segregation, because the more massive object will experience more friction and therefore start collecting in the center. It takes a lot of time, but that's a very important and interesting process. All right, so I'll go about this in many steps, and we will have to follow many steps. The first one is a reminder of the two-body problem, because we need, again, the concept of a reduced mass, the concept of the motion of the center of mass, and so on. Next step, I will remind you of the Kepler problem and the hyperbolic orbits and the angles that appear there, and so on, because we need a scattering angle. And from that scattering angle, we will derive a formula for the change of velocity of both our test mass and the small masses. And finally, we will have to do statistics over the collisions that occur. That is, we will have to integrate over impact parameters and over velocity distribution. All right, so number one. Here is a small mass. Here is a larger mass. Let's give them the masses small m and large m. And now, of course, we are interested in the equations of motion for these two masses. I hope in my handwriting the small m and the large m will be obvious enough, but if not, please complain. All right, these are obviously the equations of motion for these two objects, and if the force exerted by the force exerted by large m on small m, or the force exerted by small m on large m, are the only forces that occur, then of course they are equal and opposite by Newton's third axiom. So this will be minus f small m. Okay, So now let's simply take the sum of these two equations. And the sum of these two equations says this is m small m times x small m double dot large M times x large M double dot equals 0 because of Newton 3. But this is almost the definition of the center of mass. And if you divide this expression by the sum of the two masses, then this is the acceleration of the center of mass, which is 0. So obviously, if you don't have other forces, if you don't have external forces, just the forces between the two particles, then the center of mass will move on an inertial trajectory. And I'm going to use that to conclude that small m times v dot small m plus large M times v dot large M equals 0. Well, this is obvious. That's just rephrasing that. And from that I conclude that any change in the velocity Vm of the large mass is going to be minus small m divided by large M times the respective change in the velocity of the small mass. Okay, this is nothing new, I guess. Now let me do a different operation. Let me multiply this with capital M, this with small m, and then take the difference of these two. Equations. So that's what we do. Then I take the difference, and the difference then reads this product of masses. Now the relative acceleration of the two. Now by taking the difference, I get I get 1 time the force Fm multiplied with capital M, and I add the force Fm multiplied with small m. So I have all right, and this leads you to the reduced or to the two-body problem, right? You introduce the reduced mass, the relative acceleration, and see that this is the original force Fm. Okay, you know all that. I just need to remind you of that. And mu, of course, is the reduced mass. And I'm going to use that to introduce the relative velocity, which is the relative coordinate, the separation of the particles, time derived. So this velocity is Vm minus V large M. And now I use that in order to eliminate the V small m. So V small m is the sum of V and V large M. So this is this expression here. Now I can solve that for delta V large M. Bring this on the other side. Then I have this one. And what follows, let me put that in a box here. What follows is that delta V large M is this expression here, minus small m divided by large M, divided by this. So this will be minus small m divided by the sum of the two masses times delta V. Or, more conveniently, this is minus mu divided by capital M delta V. We are going to get back to that later. That was essentially the only expression that we really need from here, except for the definition of the reduced mass. And I need to remind you of the fact that this equation of the force acting in this equation of motion for the virtual particle with reduced mass, whose relative coordinate we are looking at here, is the gravitational force acting on small m. So let me write this down. I'm going to write this as alpha divided by r square, unit vector in radial direction, and the alpha abbreviates GMM, and Newton's constant times the product of the two masses. Okay. All right, this was step number one, just a reminder of the two-body problem and the relations that we derive from there. Now, next one is Kepler's problem. And let me just quote several results that we had in Classical Mechanics 1 on the Kepler problem, namely the orbital equation R of phi. So the separation between the force center and the center of the virtual particle that orbits here around the mass center as a function of the azimuthal angle in the orbital plane. This is given by p divided by 1 plus epsilon cosine phi. P is the orbital parameter. That essentially sets the length scale of the orbit through the angular momentum L and reduced mass mu together with this coupling constant alpha. And we have epsilon square is 1 plus 2 e L square alpha square mu. Okay. Now, of course, you can believe all that, or you can look it up, but I'm not going to present all of that again. Right? That's just treatment of the Kepler problem here. So this is the length scale. This is the eccentricity of the orbit, or ellipticity, also set by the ratio of energy times angular momentum squared divided by the reduced mass. All right. Now, in the situation that we have in mind, right, we sit on the mass capital M, Flixbus, okay, and small objects flying by. And we have positive energy with respect to them. Right? Otherwise we would be bound to them. Because we have positive energy, the eccentricity or ellipticity is larger than 1. Because that is the case, there's a range of angles for which this radius is undefined. Right? Of course, this radius needs to be a non-negative number. But you see that the radius as a function of phi goes to infinity. In other words, we reach the point where the masses are infinitely separate for cosine phi equals minus 1 over epsilon. And that's a characteristic of the hyperbolic orbit. Right? So the situation looks like that. We are looking on the orbital plane now from above. And we have a hyperbolic orbit like that. And it escapes to infinity under an angle defined such that the tangent to the orbit has this azimuthal angle phi, given by this equation here, when the distance of the hyperbolic, the branches of the hyperbola here reach infinite distance. All right, so here's the angle phi, defined in this way here. So this is obviously 2 phi. The scattering angle, on the contrary, would be the degree to which the outgoing orbit deviates from the incoming orbit. So the scattering angle would be this, which I now mark with a double line. So that is theta, scattering angle. And now you can simply read off that construction that theta is just 2 phi minus pi. Okay? 2 phi is the whole thing here. If you subtract pi, you get the angle theta. So theta equals 2 phi minus pi. That relates the azimuthal angle for the branches of the hyperbola escaping to infinity with the scattering angle theta. So if I take the sine of theta over 2, this is the sine of phi minus pi over 2. And that happens to be the negative cosine of phi, right? Just because it's a sine shifted by half, by 90 degrees or by a quarter of the full phase. So this is 1 over epsilon. So we have an important relation here. Sine of theta half is just 1 over epsilon. And epsilon is set by the relative energy or angular momentum of these two bodies. Okay, very well. Now I'm going to use two trigonometric relations. Again, you have a choice of either believing them or looking them up. I'm not going to derive them. One is that sine theta is 2 times sine theta halves cosine theta half. All right, sine theta we know. Cosine theta is just the square root of 1 minus sine square theta half. Okay? So you see that this is 2 times square root epsilon square minus 1 divided by epsilon squared. And we don't need to worry about this, the square root to get negative or anything, because we start from the assumption that we have unbound motion, so therefore epsilon is larger or equal 1. Okay, now cosine theta, you either take square root of 1 minus sine square theta, that's the complicated way. The other one is to use another trigonometric relation, namely this one, and say, okay, cosine square theta halves. This is 1 minus sine square theta halves, or this one here, right? And I subtract 1 over epsilon square for sine square theta halves. So this is a this here, right? Epsilon square minus 2 divided by epsilon square. Okay, now we know a lot. Now we know a lot, and now comes step number 3. Step number 3 says the following. I'm looking at, I'm working in the situation of the two-body problem. I'm dealing with relative coordinates and with a virtual particle. And this virtual particle has a single velocity. And let's say it comes along here. It has the reduced mass mu, and it comes along a certain direction, which I choose to be the x-axis. All right. Then something happens, and the particle moves away like that. We now know the scattering angle. It's this one here, right? The deviation between the incoming and the outgoing direction. And the absolute value of the outgoing velocity, right, is of course also v, right? Because we have an energy conserving situation here. All right. So that outgoing velocity has a perpendicular component which the incoming velocity did not have. And this is simply minus v times sine theta. And we know theta now. Very good. The parallel component in the outgoing situation is v cosine theta. And we also know cosine theta. Okay, so delta v perpendicular is minus v sine theta, and delta v parallel is v minus v cosine theta, so the change in the parallel components. So this is v times 1 minus cosine theta, but the cosine theta we have there, epsilon squared minus 2 divided by epsilon squared. So this is going to be, if I bring this on the same denominator, epsilon squared minus epsilon squared plus 2. So this is just 2v divided by epsilon squared. This is nice, right? Because now we know by how much our virtual particle is going to be decelerated. Right? It changes its parallel velocity component. Right? So in the parallel direction, it's now slower than before. Aha. Now what do we do with this? Let us now gradually move back from the relative coordinates of the two-body problem to the deceleration of the mass capital M. All right, but let us first see with how many of the small masses our large mass is going to collide, or on how many of them it's going to scatter. So the number of encounters is given by, okay, here we come along. Now I'm going to look at a ring around, a ring in the plane perpendicular to our direction of motion, with radius b, the impact parameter, and width db. Okay, so the area of that is going to be 2 pi b db. Per unit time, it will be passed by a number of objects that increases with the relative velocity of our two objects, v. The number density I'm going to write in this way. That's the phase space density of the objects with a small mass. And this will be parameterized by v small m. Notice, right, here we have the relative velocity. Here we have the phase space density. It's not complete yet, right? Here we have the phase space density for the objects with a small mass m, but that will be parameterized by, obviously, v small m. And not v, right? We will have to transform later. Okay, this I will have to multiply with a volume element in velocity space, d3vm. So this is the number of encounters that the mass capital M experiences per unit time because we have multiplied with the velocity here. Per unit volume element in velocity space of the small masses, and per unit width of the of that ring of width dB in the impact parameter b. Each of these encounters, of course, will cause that that velocity change here, 2v over epsilon squared. All right, so the total acceleration dvm dt that our mass capital M is going to experience is the number of encounters times the velocity change per encounter. And now I need to take into account that this is the parallel component of the relative velocity only. So I need to give this a vector arrow, right? Because I need to compare this to the vectorial direction of the velocity vm. All right, and I will have to integrate this over dB, and I will have to integrate this over all relative velocities. So one of these integrals goes from 0 to somewhere. And here we start having a problem because we don't quite know where somewhere is. And I've told you in the beginning that since you cannot shield the gravitational force, extended stellar dynamical systems have a risk of never ending. Nonetheless, let's assume that there is something like a maximum impact parameter B max here. Okay, now what in this expression that I've written down here, what in this integrand does depend on the impact parameter in the first place? Right? What will we have to integrate over? Now let me return to the definition of the ellipticity here and write it underneath there. So we had epsilon squared is 1 plus 2 energy angular momentum squared divided by alpha square mu. A situation is this line. Now I draw the situation of our two-body problem again. I have the relative velocity v, which I orient parallel to the x-axis. I have the point of smallest separation here, where the separation between the two is b. And now I can evaluate, because energy and angular momentum are going to be conserved, I can evaluate the energy and the angular momentum far away from this encounter here. And there, we will have no potential energy to take account take into account, right? Because we are going to be far away. 2 times the energy is therefore 2 times the kinetic energy of what? Of our our virtual particle with a reduced mass. Right? So don't insert capital M or small m here. It's the reduced mass mu. So that's going to be mu times v squared. Okay. What is the angular momentum? Well, this is just bv mu. Right? Because far away, let me put it this way. The vector L is going to be m times x cross p. So the absolute value of that is mrp sine phi. And r times sine phi is just the impact parameter small b. Okay? So I can use these equations and I can write the ellipticity squared, or eccentricity, I should say, squared is mu v squared times b v mu squared divided by alpha square mu. And I'm going to write this just for the sake of abbreviation as 1 plus some capital A square that we use as a trash bin for the moment, times b squared. Right, so here you see the ellipticity here is directly proportional to 1 plus something times b squared. So we need to take into account this hidden b squared dependence in the denominator here. What is A? Well, you can just read this off. One of the mu's cancels. And then we have the rest, everything of the rest squared. So this is mu v squared divided by alpha. Right, we have this awkward v to the 4th dependence here in this relation. Okay, now we are going to use that. I'm going to use this relation here to write the following. 2 epsilon d epsilon equals 2a squared b db. So I'm going to use that for a variable transform to return to this integral here. So I know from this substitution here that the integral over b db divided by epsilon square, right? This is the thing that I have to integrate first, right? Because this is the only dependence on the impact parameter that I've left. Now, what is this? This is 1 over a square divided by epsilon, right? I'm replacing b db by epsilon d epsilon divided by a square. One of the epsilon cancels, and I've got that. Okay, where are the integral boundaries? That goes from 0 to b max. All right, so that will go from 1, right, because the minimum eccentricity that I have is 1. That goes from 1 to epsilon max. And epsilon max is this relation up here that I get when I insert b max. All right, the rest is a logarithm. So this is 1 over a squared ln epsilon max minus ln 1. That's ln epsilon max. Epsilon max is 1 plus a square b max squared. So this is 1 plus a square b max square. And again, we don't quite know what b max really is. And as so often, we invent a new name for it. and hide our ignorance behind that name. It's called the Coulomb logarithm. Coulomb, because we have a Coulomb interaction, 1 over r in the potential. So this is ln1 plus lambda squared divided by a squared. Okay. What should we insert for lambda? I don't know. People who do numerical simulations say lambda between 5 and 20 is approximately okay. Your choice. The crucial step of what follows is now to say, all right, ln1 plus lambda squared is treated as a constant. And now you might cringe about that, right? Because as you see here, the lambda contains an a, the a contains a velocity squared. Now, how can you dare to say that this is a constant? Well, if you think of orbital motion around a mass m, then v square is gm over r. So if you're far away from the center of our interaction, then v square r is a constant, right? It's just Newton's gravitational constant times the total mass of the object. Right? So it's, by this argument, it's not too far-fetched to say that a times b, which contains a v squared times r, can actually be treated as a constant. Okay? We are on the way to Chandrasekhar's dynamical friction formula, and Chandrasekhar got the Nobel Prize in 1983. Not specifically for that, right? But let's just for the moment accept his argument, okay? So now I can move on here and say, I'm pulling out of the integral a factor 4 pi. I also pull out ln1 plus lambda squared. I cannot pull out the 1 over a squared because that contains a velocity dependence. But what I can pull out of the 1 over a squared is an alpha squared over mu squared, right? Because that's the constant part of the factor 1 over a squared. What is left is a velocity integral. Now, of what? We start with velocity here in the numerator. I will also have to take it vectorially into account, but here we have the absolute value of it. And we are going to divide by the square of that. So we are going to divide by velocity to the 4th power. So that contains a 1 over absolute value of the velocity to the 3rd power. Okay, and the rest remains, right? This is now this awkward velocity space integral that we still have to take care of. Okay, I suggest that we now make a little break, just as long as I need for wiping the board. I'm a little bit under time pressure, you know. Okay, so I'm going to wipe the board, and then this is what we will have to take care of. All right, that should suffice for now. Good, now we have to take care of this particular integral. And I'm going to work this out because that contains a number of integration tricks that I thought could be interesting. So now we are in step number 5, right? Now we have to integrate out the, is that already 6? Oh, okay. So we have to integrate out the velocities. Now remember that the relative velocity was given by v small m minus v large m. We have to integrate over v small m. So we have an integral of the type x minus y divided by absolute value of x minus y to the third power times some function of vector x, and we need to integrate this over d3x. Okay, if we don't know anything about the directional dependence of f, we can stop here. But let us assume, in order to move on, that f is going to be isotropic. Right? So f will depend on the absolute value of x only. That's what we are going to assume. Right? We are going to write this as f of small x. All right. This may or may not be appropriate for the astrophysical situation that you find yourself in, but let's assume that for now. Okay, if that is the case, then the whole integral looks like this, as x squared dx d phi d mu all right, f of x like this. Okay, now of course you see there are two vectors in the game. One is x, one is y, but during the integration y is constant. So let's fix y and turn it into some direction that we find good for our purposes. Right, so we rotate the entire coordinate system such that y will point into the z direction, and then the only angle we have to deal with is the angle between x and y. And then we can integrate out phi. But before we do that, note the following thing. Suppose you start with this, and now you apply a gradient. Let's say the gradient with respect to x. What is this? This is exactly this expression here, except for a minus sign. Okay? This doesn't help me a lot. But how about this? Leads to the same expression with the right sign, and has the phenomenal advantage that we are now taking the gradient with respect to a coordinate that we are not integrating over. Aha. Isn't that nice? So this means that our complete integral here can be written as the gradient with respect to y of what? X squared dx, okay, d phi so that's a massive simplification already. Okay. The phi integration is trivial by our choice of coordinates. let me order terms now. Collect everything that only depends on x here. And then write this mu integral here in the following way. Well, this absolute value is the square root of its argument squared. So x squared plus y squared minus 2xy mu. Right? That's the angle cosine between the vectors x and y. And by our choice of y, this is just the cosine of the polar angle. Okay, now in order to work this out, we can make a wonderful substitution and say, okay, this thing, I make the substitution z equals x squared plus y squared minus 2xy mu. Okay? Because then dz, for the mu integration while x and y are constant, this dz is just minus 2xy d mu. And then I have to integrate between boundaries, and the lower boundary will be what I call z plus, because that is going to be x squared plus y squared minus 2xy with mu equals minus 1. So this is x plus y squared. And not vectorially squared, right? Because the directional dependence is gone. Same thing here, right? We are z minus, that's x squared plus y squared minus 2xy, because this is the substituted expression evaluated at mu equals plus 1. So that's going to be x minus y squared. Okay, so with this substitution, this is very simple. Right? We will have to divide by 2xy, and we have to take care of that minus sign. And I do that by exchanging the integral boundaries. I would have to integrate from z plus to z minus. I take care of the minus sign by integrating from z minus to z plus. And all that remains is a dz over square root of z. Okay. That's of course the square root, the integral. So this is just 1 over xy root z plus minus root z minus root z plus, root z minus are just the absolute values of x plus minus y. So that's this expression here. And now we see, okay, you have to distinguish between x larger or smaller than y. Because if x is larger than y, you just get 2y here. And the integral is 2 over x. And it's 2 over y in the other case. So we get this result here. That's great, isn't it? What does it mean here? Well, we have to integrate over x from 0 to infinity. But now we have to take into account that this gives a different result whether or not x is larger or smaller than y. So I need to split the integration into one part that goes from 0 to y, in which obviously x will be smaller than y, and the rest. So this is the gradient of y, 2 pi, integral x squared f of x dx. Okay. First one I want to take from 0 to y. Then I need to take the branch x less or equal than y. So that's just going to be 2 over y. Let me pull the 2 out. That gives me a 4 pi here. And then I will just have 1 over y. Then I have to add the integral from 0 to infinity, in which x will be larger than y. Here I have to divide by x. I've taken care of the factor 2 already. So then I just have x, f of x, dx left. Okay, now I have to take the gradient with respect to y. But these expressions only depend on the absolute value of y. So the gradient with respect to y will be the partial derivative with respect to the absolute value of y times the unit vector in y direction. So I'm going to use this. I'm going to take care of the unit vector later and just ask, what is dy applied to these two expressions? That's the first one. 1 over y times the integral 0 to y, and plus integral y to infinity times this. Okay, now here we will need to apply the product rule. And we will first of all get 1 over y squared times the rest. Then we will have to apply that y derivative to that integral. That's going to be the prefactor times the integrand at the upper boundary. So we have 1 over y times y squared f of y, so that's y f of y. And now we have to take care of this one, but here we have to take the derivative with respect to the lower boundary and then evaluate the integrand at the lower boundary, and that subtracts the y f of y again. Lovely. So this expression here, in fact, looks very simple. This is minus 4 pi. All right, now we have to multiply this result here with a unit vector in y direction. I'm going to write this as vector y divided by y cubed. And now the integral from 0 to y, x squared f of x dx. All right, and now we are almost there, because now we can directly insert this result here into the into that expression here. So let me collect these results now. So we have from here 4 pi, and we have from up there a minus 4 pi. So that's a minus 16 pi squared. Then we have the Coulomb logarithm. Now we have alpha squared divided by mu squared. That was alpha. That's 1 over mu, and we need this squared. Now we are here, and now comes our beautiful result, which says Vm divided by absolute value of Vm to the absolute value Vm to the third power integral from 0 to Vm, Vm squared f of Vm dVm. Now we have a single one-dimensional integration left over the isotropic, assumed isotropic velocity distribution. Okay, now we sorry. All right. So this just gives you g times m plus m. And the rest. All right. We could stop at this point. And this is sometimes already called Chandrasekhar's dynamical friction formula. All right. First of all, there's a minus sign. So this is indeed friction, and it counteracts the velocity. It acts anti-parallel to the velocity itself. It depends on the mass of both types of particle, but suppose capital M is much larger than small m, right, such as a galaxy moving through a collection of stars, then this is just capital M square, and you see that it depends on the square of the mass of the object that is being decelerated. And that leads to this effect of mass segregation that I mentioned. And objects with a larger mass will experience more friction and therefore be slowed down. And this leads to the fact that massive objects gradually collect in the centers. And you can see this in galaxy clusters, for example, where the more massive galaxies are closer to the center than the less massive galaxies. And this type of mass segregation is actually observed. You can explain this in terms of Chandrasekhar's formula here. Suppose Vm is very small. What is small? What is small? This velocity distribution will somewhere have a characteristic velocity, velocity dispersion of the small objects and so on. Let's assume that V capital M is small compared to that. So then you can replace this integral here just by this expression. No, you cannot. This one here. And it's approximately that volume that this velocity Vm spans times a characteristic value of the velocity distribution within that volume. That will be approximately f of 0. Whatever that is, right, it then scales with Vm cubed. It cancels this one, and then the friction becomes proportional to, the acceleration becomes proportional to the velocity. This is Stokes type friction. If, on the contrary, Vm is very large, in the same sense as before, then you will integrate over the entire phase, essentially over the entire phase-space distribution here, and then the velocity space integral will just be this would be almost the spatial number density. It would be the spatial number density if we would integrate over the complete velocity space. But a factor of 4 pi is missing, right? So this would be the number density divided by 4 pi. And then you see, then the friction becomes essentially proportional to 1 over v capital M squared. And no and. Okay, good. So what does this mean? This means that if an object with a very high velocity comes into this distribution of small masses, the frictional force in the beginning will be very small and will enhance, it will increase over time until it finally reaches the Stokes limit. That the velocity change, the acceleration becomes proportional to the velocity itself. And what does that mean? If you have a time derivative that's proportional to the quantity itself, then the velocity is going to decay exponentially. So at first, not much will happen. And then the massive object will fall into the center. All right. But let's move one further step forward by assuming that the velocity dispersion is Maxwellian. Okay? So let's assume, in addition to what we have already assumed, that just need to wait until this is dried off, right? Let's assume that finally f of Vm is given by 1 over the square root 2 pi sigma square to the 3rd power. That's a normalization factor. Now times the spatial number density n, and what else? Exponential of minus Vm squared divided by 2 sigma squared. So let's assume that we have a Maxwellian with velocity dispersion sigma squared. Okay, now we need to work out n divided by square root of 2 pi sigma squared to the 3rd power, integral Vm squared exponential from 0 to V capital M. This would be easy for V capital M equals infinity, right? Then we would integrate over something like a Gaussian. And since that leads to a very well-known result, let me demonstrate that. So what do we have? We have a situation of the kind x squared exponential minus x squared divided by 2 sigma squared dx from 0 to y. At first I'm going to introduce a new variable t as x divided by root 2 times sigma, so that I can write this as the Jacobian cube, or the Jacobian. Now, from 0 to y divided by root 2 sigma, let me call this capital X. Now, I have t squared e to the minus t squared dt. If I had an integral of this sort, this would be the error function. That is well known. That would be nice. Right? This you can look up in any table, this you can call by any kind of subroutines. But what would that be? Let me use a trick to work this out. I'm starting with this expression here. I'm going to take a derivative with respect to lambda, or negative derivative with respect to lambda. And once I'm done, I set lambda to 1. And this gives me exactly what I wanted. This gives me this one here. Yes, gives me that one. All right. So I'm going to start with this one. This I can relate to the error function. We'll see in what way. And introduce a new integration variable, which is root lambda times t. So then, this is root lambda. Sorry. 1 over root lambda. Integral from 0 to root lambda times x e to the minus tau squared d tau. Now I need to take a derivative with respect to lambda of that. So if I take now minus d lambda, 1 over root lambda times x as upper boundary e to the minus tau squared d tau. What do I get? I get 1/2 1 over square root lambda cubed. Then I have taken the derivative of that one. So the rest remains. Okay, and now again, I have to take the derivative with respect to lambda of that one. That's first of all a derivative with respect to the upper integral boundary. I need a negative sign. The prefactor is unchanged. And then I need to take the derivative of the upper boundary with respect to lambda, and that is x divided by 2 root lambda And then I get the integrand at the upper boundary. Okay, but I need to set lambda to 1 at the end. So with this result here, I can move on and set lambda everywhere, set lambda to 1 everywhere where it appears. So this is a half times 1 times the integral from 0 to x e to the minus tau squared d tau. This is root pi over 2 times the error function, according to this definition here. And I can further subtract minus x divided by 2 e to the minus x squared, again with x equals 1. Okay. Now let me return here. I need this prefactor. Times this expression here. Let me factor root pi over 2 out. Then I have 2 times root 2 times sigma cubed times root pi divided by 4. Error function now of capital X, because that was our definition of the upper boundary, minus, okay, now when I factor out root 2 over 2 from here, I get root pi over 2, I get 2 over root pi left. The 2 cancels, this 2, x times e to the minus x squared. Okay, this prefactor here is just root pi over root 2 sigma cubed. Now I can return to our velocity space integral. So from here I now know that this expression here is given by the prefactor from the normalization of the phase space density times this velocity space integral. The velocity space integral is this expression here. There's a sigma to the power of 3 that cancels this one. And now it's the error function of capital X minus x over root pi with x now v capital M divided by root 2 sigma, right? Just the our respective variables insert. Okay. I can do a little bit of massaging here. So this, the sigma cube cancels out, the n remains. Here we have a root pi divided by pi to the 3/2. So that's 1 over pi. Here we have root pi cubed times root 2 cubed times root 2, that's 4. Okay, and now we can return to our original expression for the deceleration. We now have minus 16 pi squared divided by 4 pi, okay. We have ln 1 plus lambda squared, g squared, m plus m cubed times the number density n. Times this expression here, and this is also a version of Chandrasekhar's dynamical friction formula that you often find. Now, of course, in order to work out the consequences of this, right, in order to see how quickly does the orbit of the mass capital M decay and so on, first of all, you need to choose these masses, obviously, and then you need to choose a number density profile for the small masses M, right? Because that is what the mass capital M moves through. All right, and then you need a velocity dispersion here. So as an example, you could insert as a mass density our result for the singular isothermal sphere, for example. Right? Then the number density would be given by this divided by small m. And now you can scale all the velocities that appear here, also the velocity on the left-hand side, first of all by root 2 sigma, and you would get an equation for capital X. Then you can insert a time scale, or you can define a time scale. For example, as the radius of the entire system divided by the velocity dispersion. And then, finally, you can replace these quantities here by the total mass contained in a singular isothermal sphere up to radius r. And then you can finally replace the physical radius r by a scaled radius capital R divided by large r, and you get a dimensionless equation. You can solve this numerically. And one of these solutions you find in the book, I would like to show it to you, right? But this machine has no, maybe it has now. Has no network connection. At least it didn't have network connection. But you see the picture in the book, right? It shows an orbit of a large mass that enters into mass distribution at the top left, and then you see how the orbit decays. All right, can't help it, I'm sorry. Now, remember the approximations, yeah. Oh, I'm sorry. Sorry, I forgot about that. It's not essentially meaningless. Okay. Now, when you look at this formula, you find it quoted very often. And remember what the approximations were that entered into it. So first of all, essentially we have assumed that we can integrate out to a finite, out to a maximum impact parameter that is far away. We also have assumed we also have assumed that we can neglect the perpendicular deflection of the large mass. And the reason for that was that we assumed that scatterings to the left would be about as frequent as scatterings to the right, which means that the large mass m would be flown by as many small particles on its left and above, below, and on its right, and so on. So essentially, we have assumed that we are somewhere in the middle of that mass distribution, which, of course, in the situation that I've just described, with the isothermal sphere and so on, and that you find illustrated in the book, is essentially not correct. Right? Because then you would get a deflection perpendicular to the direction of motion. Next thing we assumed is that we can treat the Coulomb logarithm as a constant. This may or may not be true. And the right value for the Coulomb logarithm is normally determined in a numerical way, right, from setting up stellar dynamical systems numerically. Then we have assumed an isotropic velocity distribution of the small masses, which does not need to be the case. Right? Remember Teen's equation, where we specifically took into account that the velocity may be anisotropic. Then we have integrated here over a Maxwellian. We have assumed that the velocity dispersion of that Maxwellian is constant. Nonetheless, we are assuming that we can scale the whole result by a density that may be radius dependent. The singular isothermal sphere is, of course, a special case, because there the velocity dispersion is in fact constant. But this does not need the case, right? And therefore, starting with this admirable equation, right, which is really a very important result, first derived by Chandrasekhar, on this equation, there's a whole literature of what to do else. What to do else in its derivation, assuming anisotropy, assuming that you have not only these deflections, but fluctuations about these deflections, assuming that you might have a change in the perpendicular component of the velocity, and so on and so on and so forth. Okay, so you find very many modifications of Chandrasekhar's formula, but this is the point to start from. All right? Okay, so we finished Chandrasekhar's formula today. Then on Wednesday, I will at least introduce the Fokker-Planck equation. And then we are done. And now I'm running to the train station. My cell phone beeped in the meantime. I hope it's not the DB navigator again. You know the problem. See you on Wednesday.